family of types of compensators. It's an example of a way to do frequency response design. If you're in Canvas, look for this folder. It's called Frequency Response Design. Did you have to see? It's already seen. So I'm gonna kind of go over the principles of phase lag design. There is a complementary complementary type of compensator called the phase lead. The design of a phase lead is a little bit more complicated, which is why we do the phase lag first. If you're just coming in, you need to go to the back of the room and just coming in, like through the door right now, you need to pick up the sheet of paper that looks like this at the top. This is the frequency response that we looked at on Wednesday. It's an identical frequency response. I've just shrunk it down so it kind of all fits on one screen up here. And you can scribble some notes below it today. Today what I want to do is just go over the issues involved with designing a phase lag compensator. And we'll do an example then on Monday. We might start the example today, but we'll finish out the example. So what we have here, again, is the frequency response of part of a control system. And so what is given right now is that I want to remind us that we are using the frequency response design techniques we are using techniques that allow us to predict the behavior of a control system given that we have information about the plant or the process. And so this is the simplest control system diagram that we can draw, a single feedback loop, and it also illustrates the point. And so this is given, G of omega is given. G of omega is the frequency response. So what we have in our hands is maybe the output of a spectrum analyzer or frequency response analyzer, sometimes called a transfer function analyzer. Somebody did an experiment and generated this frequency response for the system. And so up here, we have magnitude versus frequency. This is the magnitude response of just this block alone. And this is its phase response over frequency. It means that the response, the output, lags the input. It takes a moment for the output to appear, which is why the response, you see the phase here, is negative degrees. Okay? And what we want to do is we want to design the control system to have certain behaviors, and we can predict those behaviors by looking at stability margins. And the last time we met, we practiced on this diagram looking at the stability margins. For example, we looked at where the phase crosses 180. Now, I had MATLAB put in this line for minus 180. So this line here stands for minus 180 degrees. And so what I can do is I can see where the phase crosses 180, and this is going to be the phase crossover. So this is one point that's important for a control engineer to be able to identify. Because then what we can do is we can come up here from the phase crossover. This is the phase crossover frequency. We have to be able to identify this phase crossover frequency, be able to express it in the correct units. It's in frequency. And then what we do is we can then take a look at the difference between the actual gain and 0 dB. So the important line here, again, is 0 dB. Now remember, 0 dB means a gain of 1. So a gain of 1 at an angle of 180 degrees is the point minus 1 on a Nyquist plot. So on a Bode plot, it's separated into two pieces, a magnitude and a phase. But on a Nyquist plot, it's 1 point is the point minus 1. So it's 1 at an angle of 180 degrees. That's why we have this line joining these two things together. This represents 1 at an angle of 180 degrees. But then we can read then the margin, which is this little bit right here. Okay? And we talked last time about how to measure that margin. Is it a positive margin or is it a negative margin? And we want to review that. The second line, the second curve corresponds to what we call proportional control. And so that would be the case where we decided to change this compensator, and we turned it to a, instead of just being no compensator, we added a compensator gain K. So last meeting, we let this compensator just be a gain K. That's what we call proportional control. Okay, it's a proportional compensator. Proportional compensation. And what we learned from that is that if we increase the gain, we're not changing the phase, so this curve doesn't change. The only thing that changes is this curve changes. It moves up and down. Now, in a few days, we're going to go back to the lab, and we're going to do this in MATLAB, and we're going to, there's some graphical user interface tools that allow us to basically manipulate these things by hand, or by computer anyway. You can do things with your mouse and make these things change like in real time. But today we're going to learn basically techniques for doing this by hand if we're not sitting in front of a computer. So what I've shown here is the case where the gain K basically increased the gain by 20 dB. You see this is right now 20 dB at low frequency, and the gain has increased to 40 dB. That's a 20 dB change. And at every single frequency point here, the gain has increased 20 dB. And so last time we met, we let K equal to 10. K equal to 10. That's the same thing as plus 20 dB. And then what we did is we went through the same process again, and we determined what was the phase crossover and the gain margin. And the gain margin changed, and the gain margin changed to be now this value, okay, instead of this one. So we had two gain margins, one associated with the solid curve and one associated with the dashed curve. And we saw that the gain margins changed. We also practiced looking at the phase margin. Phase margin requires us to see where the gain crosses over 0 dB. So again, the important point we have to be able to identify is the gain crossover. And the gain crosses 0 dB right here initially. Okay, right here. And this is called the gain crossover. We did this all last time, so you don't need to dirty your paper today if you don't want to. This is the gain crossover, GC. And we, again, draw these lines down, and from here we can determine the phase margin. This is the phase margin down here. It's kind of hard to see when we're trying to cram everything into one slide, but we practiced this last time on a bigger slide. Now, when the gain is increased, that means the gain crossover changes. Instead of crossing over here, the gain crossover occurred over here. So this was the new gain crossover. The new gain crossover is here, and that means the phase margin has changed, and now the new phase margin is down here. And the new gain crossover, this is a second gain crossover. And we saw that the gain crossover now went to the other side of the phase crossover. So when the gain crossover was less than the phase crossover, we came to the conclusion that this control system was stable. Remember, this is open loop. These are plots of open loop behavior. This curve here is a gain of G of omega. This dash curve is the gain of 10 times G of omega. And this is the phase of G of omega. It's also the phase of 10 times G of omega. It doesn't change. Okay? And so just by looking at the open loop behavior, we can predict what the stability will be of the closed loop system. And we said that if we work off the solid curves, the system will be stable. But if we decide to increase the gain, we run into the problem that we could make the system unstable. So what we really need is we would like to adjust the curves in a different manner. We want to adjust the curves in a manner that allows us to increase the low frequency gain. So this is good at low frequency, but this is now bad at high frequency. So what we would like to do is to have an adjustment that allows us to increase the gain at low frequency, but maybe not increase the gain at high frequency, or maybe even reduce the gain at high frequency if we needed to. So we're going to look today at a compensator that can do that, and that's called the phase lag compensator. Now let me introduce the phase lag compensator. This is a circuit that will do a phase lag compensator. I'll draw just two resistors in series. in series with also a capacitor, like so. Okay. All right, so this is a capacitor. Its transfer function for the is of this form, V out over V in. I can write it this way. It's going to be K, and then here it has a 0, S over omega Z plus 1, S, and it has a pole, S over omega P plus 1. Okay, so this is the lag circuit, phase lag circuit. Okay. It has a 0 at omega equal to omega Z. It has a pole at omega equal to omega P. Okay. In some of my notes, I get tired of writing omegas, so I'll just write S over Z or S over P. Okay. There are 3 parameters that can be designed: K, omega Z, and omega P. Now, what I'd like for you to do for a little bit of homework exercise, for this circuit, I want to do a little bit of circuit analysis. Find omega Z and omega P in terms of R1, R2, C. Okay. So several decades ago, if a person said, I wanted to compensate my system with a phase lag, he might come up with a network like this. We call this a network of devices. And he said, I know that I have a certain omega Z and omega P and a K that I would like. I need to find R1, R2, and C. So this is a network, and this is called synthesis. Network synthesis is basically coming up with a network that produces the desired transfer function. Today, we generally don't do R's and C's, except in specialized applications. We will take that transfer function, and then we discretize it, and then we write difference equations, which we've done for exam 1 and 2. All right, we do it with a computer. All right, let's take a look at the response of this circuit, the frequency response. We're going to take a look at the lag circuit frequency response. Okay. For your homework, please go ahead and figure out what are omega Z and omega P, and go ahead and figure out what is K for this circuit. Okay. Find omega Z and omega P and what is K for that circuit. Okay, so this is one type of phase lag circuit. There are other types of circuits that are possible. All right, so the phase lag frequency response, we're going to sketch 2 things. We're going to sketch the Bode diagram just of the compensator. The compensator is C of S is equal to K S over omega Z plus 1, S over omega P plus 1. Okay, like so. This is the compensator. It's got a 0 and a pole and a gain. Let's sketch 2 diagrams on top of each other, the magnitude plot and the phase plot. And both of these are with respect to frequency, omega. This is going to be the magnitude in dB, and this is going to be the phase in degrees. Now, the phase lag compensator has this characteristic. When omega is very small, way over here, that means S is small. Let's suppose S is really small. Then the gain is K. Okay, so that means the Bode gain is K. And so at low frequency, the gain here is going to be K, but we have to express it in dB. So we have K here. This is not in dB. We have to express it in dB. So remember that K in dB is 20 times the log base 10 of K. Okay. When we do design, we do design of K, omega Z, and omega P. But on the Bode diagram, things are expressed in dB. So if K is equal to 10, this is the number 20, and so forth. Now, I said there's a 0 and a pole. The way the lag compensator works is we have a pole right here, and we have a 0 right here. Omega p is less than omega z for a lag circuit. Okay. And so what happens is because we have a pole, we know that the frequency response is flat up until we get to the pole. And then, because it's a pole, it starts decreasing like this. And we know that this slope is minus 20 dB per decade. And then we know how to sketch the frequency response, the magnitude response of this thing. If there's a 0, the change in slope is plus 20 dB per decade, so then it flattens out again, like so. So this is the magnitude response of the phase lag compensator. There's more gain at low frequency than there is at high frequency. Or you can say, I can reduce the high frequency gain. Okay, those of us who listen to music, we are familiar with a graphic equalizer. It says that I want to increase the bass and I want to reduce the treble response. Okay? Now for music, this is all we care about. We've just increased the bass and reduce the treble response. But in control systems, we have to worry about this part here as well because it affects the stability margins. Now, if we take a look at the response here in the phase plot, we know that there are additional corners. There's a corner a decade below omega p and a corner a decade above. Okay? And so what that means is that the phase is going to initially be at 0 degrees, and then it's going to start coming in, and then it's going to start going down like so. Okay? And we also know that the omega z, the 0, introduces 2 corners, maybe one a decade below and another one a decade above. So there are a total of 4 corners. There's a total of 4 corners in the frequency in the phase responses. One here, one here, one here. And going through the same steps that we've done before, when we sketch the phase response, we said, oh, there's a corner here, there's a corner here, a corner here, and a corner here. Okay, something like this. The actual response curves will be something smoother. It looks like something like this. But the hand sketch looks like this. Okay. And if we want to get an idea of scale, minus 90 degrees is somewhere down here. Okay. And so you see that the phase response of the lag compensator, this is the phase response, it's always lagging. Okay, the phase, the angle is always less than 0 degrees. It's negative. The output always lags the input. That's why we call it a phase lag compensator. Let's come back to our circuit for a moment and take a look at it. This is our circuit. Okay. Let's do a little bit of quick analysis. Let's see what happens at omega equal to 0. At omega equal to 0, what is this capacitor equivalent to? An open or a short? It's an open. Okay? So if that's an open, no current flows through here, no current flows through here. Since there's no current flow through there, there's no voltage drops. So how big is this compared to this? It's the same, right? So it's a gain of 1. Now at high frequencies, what is this? It's a short. So if it's a short, what does that look like? A voltage divider. And what do we know about a voltage divider? The output is bigger or smaller than this? Smaller. Okay? So that's what we have here. We have, at low frequencies, a gain of, in this case, for our circuit, a gain of 1. And at high frequencies, a gain that's less than 1. Okay? And we can imagine, from what we remember, is that, remember that we have a capacitor. It takes a little bit of time for the input voltage to charge the capacitor before we get a response. So that's why the output lags the input. Okay, so now Now that we just analyzed that real quick, you know what is K for this particular circuit. Okay, you still got to figure out what is omega Z and omega P, I'm sorry, in terms of R1, R2, and C. Okay, so this is the phase circuit's frequency response. Okay, so kind of a bit of a summary, some notes. Some notes about phase lag. The first note is the low frequency gain is greater than high frequency gain. Okay, so if we're interested in improving low frequency gain for some reason, for example, we want to reduce steady state error, we can reduce steady state error a phase lag compensator would be a logical choice. Okay. The second thing that we see, though, looking at this phase characteristic, is we say that the output lags the input. Okay, the output lags the input. There's always, it increases the delay of the system response. Okay? This is not good in general. Okay? Sir, your homework assignment is late. Is that a good thing in general? Generally not a good thing. Okay? You're late for the bus. You're late for your date. These are generally not good things. Okay? The delay of a system is generally not good in general. This is generally not a good thing. Okay? In a few days, we're going to look at the opposite of the phase lag, a phase lead. Oh, you're early for your doctor's appointment. That's good. Maybe you can skip in line and get ahead. Okay, so in music, all we care about is feeling the music. We want to increase the bass response maybe and reduce the treble response. But in control systems, we have to worry about this. So let's take a look at, I wish I had this, I'd drawn this on a transparency, but let's come back to this picture. Our challenges here are we want to increase the low frequency gain, but we saw that when we increased the low frequency gain, we messed up the stability margins. And so what we want to do is we want to put this type of behavior, this phase lag behavior, onto the circuit, into the system. So we're going to modify the diagrams, but we have to realize that when we put this on here, it's going to reshape the curves. It's going to reshape the phase, the magnitude curve, so that we can have more gain at low frequency and less gain at high frequency. But in the control systems design, we have to also be aware that when we do that, we also reshape the phase response. And so this curve will be reshaped. And so the key idea with phase lag compensation is that we want to increase the low frequency gain do not hurt the stability margins. Okay, increase the low frequency gain, but do not hurt the stability margins. Now, for a phase lag design, this is fairly simple to do. It's not too difficult with phase lag. Did I say lead? I meant phase lag compensator. The reason it's not too difficult with phase lag compensator is because one of the characteristics that we desire is occurring at low frequency. We want to increase the low frequency gain, but we don't want to hurt the stability margins. So it's not too difficult to design this because we have a separation between low and high. So basically we're saying that it's not too difficult to achieve these goals with a phase lag compensator because the low frequency behavior gain, the gain increase that we want, is separate it's separated from the high frequency behavior. The high frequency behavior is the stability margin. Okay, let me try to express that again in a picture. The moment somebody says stability margins, I say go find the stability margins, we immediately look this way. We look at where the phase is crossing 180, and usually for physically real systems, that's going to happen at a higher frequency than it is at a lower frequency. Okay, so we start looking this way. You look at all the stability margins measurements we're making. They're happening out here at higher frequencies. But increasing steady or improving steady state error, for example, I say I want less error at steady state. That's happening at low frequency. So basically what we're saying is we have to our advantage the fact that we want to improve something over here, and we want to improve something over here, and they're kind of separate from each other. Separated. Separated from each other, and so that makes life a little bit easier. Okay? That makes life a little bit easier. We can get this. We're going to increase the gain in the gain plot. We're going to reshape the gain plot by picking some omega p and omega z, and it's going to reshape this. We're going to get more gain at low frequency and less gain at high frequency. But as we put this in, we have to realize that this curve will also reshape, but we just need to make sure that when we put it in, it doesn't mess this up. Okay? And so we need to know qualitatively anyway, what happens when we put in a p and a z like this, where the pole is less than the zero. If the pole is less than zero, we're going to get a lagging characteristic. And we just need to make sure that when we reshape this, that we don't mess things up out here. All right, there are some notes in this folder called Frequency Response Design. It tells you how to go through step by step how to design a phase lag compensator, and there's some examples. But what I'm going to do right now is I'm going to go through and write down the steps that we need to do this, and then we will do an example next time we meet in class. And so here are the steps to design. Okay, these are the design steps for the lag compensator. Why do we use the lag compensator? We typically use a lag compensator because we're trying to increase the low frequency gain. The low frequency gain is greater than the high frequency gain. So maybe we're trying to improve the steady state behavior, or maybe we're trying to reduce the high frequency noise or something like that. So the first thing what we do is we have three parameters to design. So the first thing we do is we set gain k. We pick a number gain, k. Okay. We usually do this typically maybe to meet a low frequency performance requirement. Okay. So back to our example here, we originally have this magnitude plot, this solid curve, and this phase plot. And we analyzed it, and we did this on Wednesday. We analyzed the steady state error. It turned out to be a certain number, and it wasn't, say, small enough. We said we want to reduce the error by a factor of 10. So what we did is we made k equal to 10. So in our example, that's what we did. We set gain k equal to 10. So the first step is to do a proportional control, and that's going to increase the gain. That's going to basically put in a compensator that allows us to increase the gain. Now the next thing we need to do is, figure out, pick the desired gain crossover frequency. Okay. What do we measure at the gain crossover? What stability is margin? What is measured at the gain crossover? It is the phase margin, right. We pick a desired gain crossover frequency, and this is based on desired phase margin. Remember, phase margin is measured at the gain crossover. So we will look at this plot and we'll say, what is the desired margin? See, initially we started off with this margin. With proportional control, the margin became that. That's not good. So we had to look at this curve and say, what is my desired margin? I want to stay away from 180 degrees. So I got to pick a margin. Somebody says 60 degrees, so I got 60 degrees above that. That's my desired margin. Okay, we got to pick it. Now remember, when we put in this phase lag, it's going to reshape things. Okay, it's going to reshape things. So the z, omega z, and the omega p need to be wisely chosen, because we're going to introduce more lag into the picture. We'll never introduce more than 90 degrees. The amount of lag that you introduce will be dependent on the separation of omega z and omega p. It'll never be more than 90 degrees. And so you can get an idea looking at the scale. You say, okay, 90 degrees is this much. So it's going to reshape things. Things are going to dip down. It'll never dip down more than 90 degrees. But I need to make sure it stays away from where I am making my stability margin measurements. Okay, so the first thing we do is we pick a desired gain, and then we pick a desired gain crossover frequency. The desired gain crossover frequency, let's give that name. Let's call it omega 0. 0 meaning 0 dB. In some of my notes, sometimes I call it omega 1. It means a gain of 1. Okay. This is gain of 0 dB, a gain of omega 1. I got to pick some place. I got to pick some frequency where I get the desired margin. Okay. So suppose I want, say, 120, a 60 degree margin. That's a very common number, is 60 degrees. It says right here. So I said I want the margin to be here. It was here with increased gain because this, but this is where I want it to be. So I pick a omega 1. Somewhere out here, I will pick an omega 1 or omega 0. 0 dB, gain of 1, the same thing. Okay, depends on what units you want to work in. So you pick a number where you get the desired margin. So pick a desired gain crossover frequency based on the desired phase margin. Okay, so I want my stability margins to be right here. Now the actual stability margins are not there though. They're not there because the gain crossover is actually occurring here before compensation. It occurs here with proportional control, but with phase lag control, I'm going to reshape the curve so that the curve goes through 0 dB right here at that point. So that's our objective. So we do this by picking omega p and omega z in a wise manner. So we know that when we put in omega p and omega z, it's going to cause a lag in the phase somewhere here. I need to pick omega p and omega z relative to omega 1. And this thing is also going to reshape itself depending on my choice of omega p and omega z. So what do? I don't want to mess up the measurements here. I know that I will mess up the phase. The curve will be reshaped, but I don't want to mess up this. So what do? omega p far away from this. And omega z be a dip in to get away from this, because this is where I'm making my stability measurements, my margin measurements. All right, so we set the gain k, we pick the desired gain crossover frequency. The next step is very easy. Omega z is equal to simply omega 1 divided by 10. Okay. Basically what this does, it's going to puts the lag far away from omega 1 or omega 0, the gain crossover frequency. I want this gain crossover to be somewhere around here so that I get the desired margin. But when I introduce the phase lag, it's going to reshape the curve. I don't want it to reshape the curve while I'm making a measurement right here, so the idea is let's put the lag way over here. So you just take this number and divide by a factor of 10. Okay? That's 1 decade. And right now on my scale, 1 decade is about this much. So that puts omega z right here. Okay. Now, as a fourth step, the last step we need to do is, all right, we got k designed, we got omega z designed. The last thing we have to do is we have to design omega p. Pick omega p to achieve desired high frequency loss. What do I mean by high frequency loss? If we look at the phase lag compensator, we say, hey, the gain at high frequency is lower than the gain at low frequency. This is a loss. As frequency increases, I'm losing gain. I'm losing gain at a rate of 20 dB per decade. So what I need to do is I need to say, I look at this curve, plot, and I say, look, I want the phase margin to be right here. If the phase margin is right here, the new gain curve needs to cross over 0 dB right here. It needs to cross 0 dB right here. And what I'm saying is that I've increased the gain 20 dB. I need to start losing gain. I need to start losing gain until it finally crosses here at 0 dB. That becomes my phase margin. I've already picked my omega z here. I need to pick omega p big enough to get the desired loss. So how much loss do I need? I need this much loss. It's too high right now. I need to lose this. This is the desired loss. So this, we measure the difference between that and 0 dB. This is the necessary high frequency loss. Okay? I need that much loss. So I have to work off the adjusted curve. I have the original curve. First thing I did was I adjusted gain k. So that means it gives me a dash curve. So now I'm working off the dash curve. I'm going to put in now an omega z and omega p, a combination that gives me the desired loss. Okay? So we pick omega p to achieve the desired high frequency loss. And so it turns out that omega p is equal to omega z divided by the desired gain loss. Now where this is the desired gain loss, the desired high frequency loss, that goes down here. Now, it turns out when we do this, make sure this is not in dB. In a class S size, half the students will make this error. They'll come here and they'll say, how much loss do I need here? How much loss do I need here? I want the new curve to go through 0 dB right here. It looks like that's about 20, 30, 35 dB. So they say, I need 35 dB. So they come into the formula and they say omega p is equal to 20 omega z divided by 35. Okay, and that's the error they make. You have to convert 35 dB out of dB and then put that number in. Okay, so these are the design steps. It's described in a write-up also in in Canvas. So I encourage you to take a look at it. What we'll do is on today's Friday. Yeah, on Monday, we'll go through these steps with an example. All right. So we're going to come back to these same pictures. I'll hand out a clean sheet again, and we'll work on this. We'll come up with some design specifications to work toward. But that'll be our goal. Okay, any questions? Okay, remember that admin notes, the administrative notes, is that exam 3 has been moved to next Friday. The calendar has been corrected. And our goal is to try to finish up before Thanksgiving.